chemical potential means basically you can in a layman language you can understand that how much potential an element or a constituent of a system has to affect the chemical system. Okay, there is a chemical constituent. Okay, constituent, n number of constituents are there in a reaction or in a system. So if I'll consider from one constituent, consider Ni. Okay, what it how it affects, not how, to what extent it affects the reaction. Okay, to what extent it affects the reaction or its presence, what the reaction is how the reaction is affected, to which extent the reaction is affected by its presence. That is the chemical potential of this constituent. Like you can say, what is your potential? So you can carry up to a 30 kg uh, rice bag. Okay, that is your potential. Okay, like that, what is the potential of this constituent in that chemical reaction? That is only the chemical potential. But how will we measure? How will we measure the potential? So for that purpose only, it is considered in energy. Okay, it is considered in energy, change in energy. Okay, change in energy. Now the thing is, you are carrying, you can carry a 30 kg rice bag. Now another person comes and helps you. Now you can carry a 50 kg rice bag, na? So the 20 kg rice bag, the amount of 20 kg has increased. Sorry. So that is the potential of the second person. Okay, that is the potential of the second person. Like that, in chemical, in your chemical potential, it is measured in energy. Okay, mu I. This is mu I. Yeah? Mu I. Mu I. So it is called as mu. It is denoted by mu. Okay. So chemical potential of thermodynamic system can be defined as the amount by which energy of the system would change. Energy of the system would change if an additional particle is included, keeping entropy and volume fixed. Okay, internal energy should be fixed, entropy and volume fixed. Okay, so we'll just add another particle, and what the change in energy occurs, that will define the potential of the uh, chemical reaction. Or these equations are not coming in here. The chemical potential formula is mu I is equal to du by dni. Okay, du by dni. Du is the internal energy. Okay, internal energy, and du is the change in internal energy. Okay, change in internal energy, and your mu I is the chemical potential. This S means constant entropy, constant volume, and previously constant your previous Ni is the number of constituents. Okay, number of all constituents particles, dNi. So this is chemical potential. Everyone understood how this chemical potential is measured? Okay, we have no any phenomena to measure except the energy change. How the presence of this particle affected the change in energy or affected the energy of the system, that is only measured by the chemical potential. Okay, so all chemical potentials are, energy also gives free energy is there. Okay, so all the chemical potential is partial derivative of Gibbs free energy. Like you can say mu I is equal to dg by dni at constant pressure, temperature, and number of constituents. So in case of du, you can also use dg. Okay, g is the Gibbs free energy. These are all simple equations, nothing else. Okay, so for a pure phase partial molar free energy, what happens? This dni becomes 1. Okay, this dni becomes 1, and change in energy also is constant, so mu I is equal to gi. It is not required actually, so you can learn this, that your chemical potential is equal to change in internal energy by change in uh, by the number of particles. Okay, by the number of particles at constant entropy, constant temperature, pressure conditions. Okay, so also in case of equilibrium, in case of equilibrium, in case of equilibrium, if I'll try to add some extra particle, okay, then the equilibrium will remain there, or equilibrium will be disturbed. Anyone? If there is a reaction, this is under equilibrium. Okay, so I have added a external particle. So the equilibrium will be disturbed. But according to Le-Chatelier's principle, the equilibrium will react in such a manner that it will try to always restore the equilibrium. Okay, it will try to always restore the equilibrium. That is the thing. Okay, so according to Le-Chatelier's principle, what he said? He said, if you disturb any equilibrium, it will react always in a manner that it will try to restore the equilibrium. Okay. So likewise, if there is constant number of particles, okay. So if change in at equilibrium, this dg will be 0. Okay, because there will be no change in energy in case of equilibrium. So their chemical potential we can not measure. Their chemical potential becomes 0, which is not true. So in case of equilibrium, we cannot measure. Okay, that is the thing. Okay, everyone understood this? So temperature and composition. This is not required actually. Okay. Next is your fugacity. Fugacity, you all already know that what is fugacity. Fugacity is basically the partial pressure. Okay, the partial pressure of any volatile. Okay, or to be very precise, we just consider, because the presence of oxygen is so much a matter to us, so we consider fugacity as the partial pressure of oxygen. Okay, we write it as FO2. Okay, fugacity of oxygen. Like it can be FCO2 also, like it can be FH2 also. Okay, but the fugacity of oxygen is so much important for us, so that we write that fugacity represents the partial pressure of oxygen. Okay, so fugacity F is equal to gamma into P. So P is the partial pressure, P is the partial pressure, gamma is the fugacity coefficient. Fugacity coefficient. Okay, so this is fugacity. Another long equation for fugacity is there. Okay, which we cannot actually memorize that equation. That's why I have not added this. This is the simplest equation that can, this gamma can be na, this gamma can be expanded. The gamma actually expanded to so length. Okay, so what they have done in some books, they have represented the whole equation by gamma except the partial pressure. Okay, so this gamma is called as fugacity coefficient, and P is the partial pressure. Okay. So next, fugacity measures the tendency of gas to expand on escape Fugacity is the pressure value needed at a given temperature to make properties of non-ideal gas satisfy the equation for ideal gas. Okay. So fugacity is the pressure value needed at a given temperature to make properties of non-ideal gas satisfy the equation for ideal gas. So PV is equal to nRT will be satisfied. That fugacity, pressure or fugacity that helps. Okay, this thing I didn't know actually. Okay, so everyone getting it? Okay, next is your activity. Okay, activity. Okay, activity can be like so you can imagine that activity can be like um, I will go back to that same example that you have carried a 30 kg bag and your friend comes and he helps to carry you a 20 kg bag. Now, if this your friend, okay, if your friend has a capacity of carrying 50 kg bag, okay, so adding your 50 kg plus 30 kg, so it should be 80 kg, but you two are carrying only 50 kg. Okay, so now this difference, now the difference, he has 50 kg capability, but he is active in carrying 20 kg bag only. That is the activity. Okay, that is the activity. Like how much you can say simply from the term that how much active is the constituent is. Is it in its full extent or in how much? Okay. So that's why it is also a derivative of chemical potential only. So you can say activity of a component I in a phase A can be defined as the difference between chemical potential of I in A under specified temperature pressure condition. That is the thing. Every chemical thing is under different definite temperature and pressure condition. Okay, so the difference between the chemical potential of I in A under specified temperature pressure condition. So when we under definite temperature and pressure conditions, the potential of a constituent changes. Okay, so that the difference is called as the activity. Okay, so you can see AIA is equal to PI minus PI0. So PI0 is the partial pressure at original, and it is the changed partial pressure. So let me check this. PI0, it is not written here. Okay, so mu IA, consider mu IA is the chemical potential of I constituent in phase A is equal to mu 0 chemical potential of I constituent in original phase plus RT ln Pi by Pi0. So Pi is the partial pressure, okay, partial pressure of constituent I now, okay, and Pi0 is the partial pressure at beginning, okay, at beginning, okay. So in different environments it will be like you are running 1 kilometer in 1 kilometer uh, the in the roads, okay, in the roads, but you cannot run 1 kilometer in the sands na. So that thing is defined by this activity. Okay, so you have carried 50 kg, you have your friend have carried 20 kg, but he has capacity of 50 kg. Okay, but the environments are not supporting him. The environments are not supporting him, that's why he can only carry 20 kg. Okay, so that is the difference, and that is called as the activity. How much active, dependent on the temperature pressure only. If the temperature pressure changes, then it will again your change its activity. Okay, so AIA is equal to pi minus pi 0, and in case of your in terms of chemical potential, you can say mu I is equal to mu I 0 plus RT ln pi by pi 0. Apart from that, there is a small equation also, like your uh, fugacity. Okay, AI is equal to sigma into pi. Okay, AI is equal to sigma into pi. So AI is the, write it down, it is not written here. Okay, AI is equal to sigma into, here it is written, AIA is equal to, yes, this one only. Okay, sorry, this one only. AIA is equal to gamma I into XIA. Okay, this one. So here AIA is equal to activity, gamma is equal to activity coefficient, number of crystallographic sites which mixture took place. Okay, this is then, this is not the expression. Okay, here it is not written actually. Here it is not written. Huh? So I am writing it down. AI is equal to, consider it as sigma, the previous one in pi. Okay, so AI is equal to activity, sigma is equal to activity coefficient. Okay, and pi is the partial pressure. Okay, 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 we'll not stop the recording, you will see. Okay. So this is activity. Okay, then your activity and composition relation. Activity and composition relation is how activity and compositions are related to each other. Okay, this can be described by two simple equations for ideal solution, for non-ideal solution. Okay, for ideal solution, those who follow PV is equal to nRT real gas equation, and all other yeah, Boyle's law, Charles law, these are also followed by ideal equation, ideal solutions. Okay, ideal gases, ideal solutions. So there are two activity composition relation. They are also there are also derivations of this activity composition relation. Okay, so I don't think these things are required, so I have not given. Okay, they are so you can like just memorize these equations, that how activity and compositions are related. Okay, the activity is your for your activity is the effective concentration of a component in a phase. So for ideal solution, mu ij is equal to mu ij0 into RT ln xi. Okay, mu I is the chemical potential of I and J, R is the real gas constant, T is the temperature, X is the composition. X is the composition. Or you know X is the mole fraction. Mole fraction is the composition only. Okay, so this is the relation. For non-ideal solutions, this is activity is equal to gamma into Xi. Gamma is the your, okay, this one number of crystallographic sites which the mixture took place. This thing I am not getting it actually. activity where activity yes, yes. This was the correct expression. Earlier I was telling that na AI is equal to P into sigma into Pi. This was only the correct expression. Yes. Sorry for the inconvenience. So this was only the correct expression. AI is equal to gamma ij into xij. Okay. Here this is activity coefficient, and this is the composition, not partial pressure. This is the composition. Okay, this is the correct relation. I am not actually, I cannot see this part, in my screen, na, these parts I cannot see. Okay, here my that writing thing is there, and also this part. Also this part I cannot see. Okay, that is the problem. Okay, so you just correct it down for non-ideal solution. This thing is always used for non-ideal solutions. This thing is always used, and in common also, all solutions are non-ideal solution. Ideal solution is only a hypothesis, na. Sorry. Okay, so this is for non-ideal solution. Memorize this equation. In case of activity, you can also write it down. If there is a 5-mark question called as activity, tell me about activity. You can just write it down that activity is this. It is the difference between chemical potential of a particular constituent in the defined temperature and pressure in a particular phase, and it can be defined, it can be mathematically expressed as AI into sigma I into xi. AI is the activity, sigma is the gamma is the activity coefficient, x is the chemical composition or mole fraction of the particular component. Okay, this thing is enough. Like in your fugacity. Okay, like in your fugacity, this is also same formula, na. Activity and fugacity have same formulas. Okay, so everyone getting it? थोड़ा कंफ्यूजन हो रहा होगा, मैं समझ रहा हूँ, नया चीज है, ठीक है, लेकिन एक दो बार पढ़ने में समझ में आ जाएगा, ठीक है. Okay, so next we are getting to tracing the chemical reactions in PT space. Tracing the chemical reaction in PT space. So what we do generally we in PT space, the thing is, you know the PT space. This is PT space. Okay, this is simply a PT space. Okay, so every reaction or every reaction, you can say reaction, or you can say every rock, every rocks are already the products of reactions only. No, rocks are also the products of reactions only. The rocks or every reactions are stable or not stable. They can be defined by this PT space. Okay, if we will trace these reactions in PT space, like like diamond. Diamond is not stable at Earth's surface. Okay, diamond is not stable. It is like metastable. It is called as metastable. Okay, kimberlite also metastable. Okay, they are also metastable. Okay, stable. Which things are called as stable? Which are in equilibrium, or which are in equilibrium, or they are, we can call, they are not reacting. Okay, so what happens in case of diamond or kimberlite, you can say the सी जो डायमंड है वो रिएक्ट कर जाता है एंड कार्बन डाइऑक्साइड बनाता है, कंटिन्यूअसली बनता चलता है. ओके, this is very small amount, that's why you cannot observe it, like we particularly in naked eye, or we cannot feel it. It's like experimentally we can prove it that it releases carbon dioxide. Okay, so like Olivine is also metastable in earth surface, that's why it weathers so fast. Okay, that's why it weathers so fast. So this, which reaction is stable, which reaction is metastable, which reaction is not stable, this thing can be can be found out from the PT space. Okay, if we will plot a reaction in the PT space, so how we will plot the reaction in a PT space? So this is basically done by taking a temperature. Okay, this is basically done by taking a temperature or pressure, which a single one. Okay, a single variable P or T I'll take. Okay, I'll take and I'll try to carry out that reaction, and I'll wait until the equilibrium. Okay, until the equilibrium. So one time I will keep my pressure constant. Okay, I'll keep my pressure constant and let the reaction to be begin, and I'll wait at what temperature this reaction is getting in equilibrium. So I will get a PT coordinate. So I will plot here, this here at this temperature, at this pressure, the reaction got equilibrated. Okay, now I'll change the pressure to a higher one. Then I will continue the reaction. Then I will note the temperature. I will get another point that for this pressure, for this temperature, the reaction is in equilibrium. Okay, now I can plot this. Okay, I can plot this line. This is the reaction boundary. This is called as a reaction boundary. Okay, reaction boundary of this equation, and this reaction boundary denotes what? The line of equilibrium. The line of equilibrium. Okay, if we will consider this is x plus y, this is y plus sorry z x plus y, z z plus a. Okay, z plus a. Then x plus y is in equilibrium in with z plus a at which are on this line. Okay, on this line. So this line is stable. This line is stable. Apart from these things, they are unstable. So instability increases as you go away from this line. Okay, instability increases as you go away from this line. This is very simple. Just take one pressure, constant pressure, note down the temperature at equilibrium, then increase the pressure, make it constant at some point, and just note down the temperature at the equilibrium point and join the line. Okay, so this is the tracing chemical reactions in PT space. ओके, पीटी स्पेस में टेस्ट कर देने के बाद हमको पता चल जाता है कि कौन सा स्टेबल है, कौन सा अनस्टेबल है, ये सब चीज पता चल जाता है. ठीक है, those reactions not is always line, this can be curve also. Okay, I have just given you example that it will be example for a line. Okay, so this is the thing. Everyone understood how these reactions are plotted in PT space? Very easy thing it is. Okay. Okay. So this was only written, yes, on this line, all the reactions are in equilibrium condition. For equilibrium condition, del G is equal to 0, you know. Change in Gibbs free energy. Change in Gibbs free energy is 0. Okay. So that's only written here. dP is equal to 0. We can calculate pressure corresponding to some chosen temperature where we can find del G R 0. Okay, by equation. So we know that del G R 0. So this is just a equation that denotes that del gr will be 0. This equation proves that. Okay, it is not important, it is written here. Okay, so for any point such as T, E, P, E on the reaction boundary, the free energy change in the reaction del G, okay, is equal to 0, equilibrium condition. Okay. Okay, this is the reaction boundary for Bruchsite and Pericles reaction. Okay, Bruchsite and Pericles reaction. Bruchsite is gives Pericles plus H2O. This is the reaction boundary. Here, for this temperature pressures, this reaction is in equilibrium. Apart from this temperature pressure, they are unstable. Okay. The more we go away from the line, the more the unstable the reaction is. We can just like now the diamond. We can just go to the field and note down the temperature and pressure where the diamond was placed, and we'll just plot here. We'll just plot this pressure and this temperature, and this will be like here, and this we'll know that this is metastable, this is not stable here. Okay, a simple thing. Okay, Gibbs phase rule and mineralogical phase rule, we'll come back to it later. We'll go to the Clausius Claperyon equation. Okay, so Clausius Claperyon equation, what Clausius Claperyon equation tells. So we can just derive Clausius Claperyon equation from a equilibrium concept. Consider this is a system. Okay, so here there is a x plus y components. Okay, or simple consider x components. This is y components. Okay, this is y component. They are in equilibrium condition. They are in equilibrium condition. Okay, they are in equilibrium condition. Equilibrium condition means the number of x converting to y is also equal to number of y, x converting to x. Okay, number of y converting to x. This is the simple thing. So you know that del G is equal to P del V minus T del S. Okay, gives free energy is equal to, you have studied about this na, so sir taught you na, taught you the gives free energy. Okay, so del G is equal to P del V minus T del S. So now for equilibrium we know that del G is equal to 0. Okay, for equilibrium we know that del G is equal to 0. So simply we can put here P del V minus T del S is equal to 0. Okay, is equal to 0 for this is equilibrium. So let's arrange this. P del V is equal to T del S, implies that P by T is equal to del V by del S. This can we write. Okay, this can we write. But this is only for this equation. Okay, only for the whole system. Okay, when we consider S by V. Okay, sorry. Del S by del V. Okay, del S by del V. Okay, P by T del S by del V. Clear? Okay. So now if we will consider a small component or a small change in small difference in temperature and pressure, then this will be like your dP by dt is equal to del S by del V. Okay, this is the Clausius Clapeyron equation. Simply Clausius Clapeyron equation. Okay, dP by dt is equal to del S by del V. Simple, del G is equal to P del V minus T del S. you just put del G is equal to 0 because it is in equilibrium. Okay, the system is considering the system is in equilibrium. Now just rearrange the equations and you will get your Clausius Clapeyron equation. Okay. Clear everyone? Okay, dp by dt is equal to dg by dt del h by dp by dt is equal to del h by t del v. Okay, Roflora del h p del v. So your this thing your Clausius Clapeyron equation is a way to describe discontinuous phase transformation between two phases of matter of a single constituent. A straight line does not exist between a liquid temperature and its vapor pressure. The slope at any point of a boundary curve is given. Okay, this thing I am telling you. So when we have plotted this reaction, this PT space, when we have plotted this reaction in this PT space, so this thing actually is not straight. Okay, this thing actually is not straight. Okay, like you can say, I am telling you that thing only that time that I have plotted this straight, but this is not actually straight. This is a curve. Okay, this is always a curve, not a straight equation. So Clausius Clapeyron, after plotting this reaction in a PT space, what Clausius Clapeyron done? They given equations that we can calculate the slope. We can calculate the slope of this curve at any point. Okay, at any point. So how will we calculate? By this formula, dp by dt is equal to del s by del v. Okay, del s by del v. So del s is, you know, del s, the formula of del s. एंट्रोपी का इक्वेशन क्या है? सॉरी, एंट्रोपी बोल रहा हूँ, क्या है? डेल एस. हाँ, एंट्रोपी का इक्वेशन क्या था इसमें? इसमें डाल देंगे तो ये चेंज हो जाएगा इसको. क्यू रिवर्सिबल बाई टी था ना डेल एस का, क्यू रिवर्सिबल बाई टी. एंट्रोपी इज एच बाई टी ना, क्यू रिवर्सिबल बाई टी था, क्यू रिवर्सिबल बाई टी. dq by dt, yes, that thing only, q by t. Okay, q reversible by t. H is enthalpy, h is enthalpy, and your t is temperature. So dp by dt is equal to del h by t del v, p del v minus t del s, p del v minus t del s. So if we'll change this, if we'll rearrange this, p del v is equal to t del s. Okay, dp by dt is equal to del s by del v. So del s we can represent as q by t. Let me check the formula for entropy. Formula for entropy. Q रिवर्सिबल बाई टी, तो वही तो होता है. ये here del g is equal to h minus t del s na, also h minus t del s. This h is p del v, enthalpy is p del v. Okay, so del g is equal to, if del g is equal to 0, okay, here, okay, so del g is equal to h minus t del s. Okay, h minus p, sorry, h minus t del v, p del v. So this is P, your H minus T del S, sorry, H minus T del S, del G is equal to H minus T del S. So here del G is equal to 0. So you can write I will take this as P del V minus T del S. Wait. This equation, okay. dp by dt is equal to del H by, it should be del H by T del S. Okay. So, basically you can write it down the equation of Claussius Claperyon equation, that dp by dt is equal to del S by del V. Okay, del S by del V. You can write this. I have derived this equation. You have seen, yeah, earlier I have told you. Okay, so wait. Sorry. So now you have dp by dt is equal to del S by del V. Also dp by dt is equal to del H by T del V. Okay. So now what Clausius Clapeyron did, he said that we can calculate anywhere the slope of this reaction. Okay, the slope of this reaction. So how will we calculate the slope? We will calculate using this thing. Okay, dp by dt is equal to d. This dp by dt is the slope. dp by dt is the slope, na? Here this is p, this is t. So p by t is the slope. Okay, so we can, using these variables we can calculate, or using these variables we can calculate the slope easily. Okay, so this is the slopes of metamorphic reaction. When, let's read it out what other thing has written. I have not read this. Okay, so when the reaction boundary is curved, the slope at any point of the boundary of the boundary is the slope of the tangent to the curve at that point. If del H, del S and del V can be assumed to be constant, that is independent of temperature and pressure, the slope will be constant. That is, the reaction boundary will be a straight line. Okay. So it is telling that if we will assume that del H, del S and del V are constant, then the reaction will be a straight line, because everywhere I will get a same slope. If everywhere I will get a same slope, then it will be, Suraj, anything you are telling? So that will the thing. Okay, so it will be a straight line. Okay, but every straight line, every reaction does not follow straight lines. For many reactions involving only solid of constant composition, this is a reasonable assumption over limited pt range. In such cases, all that is needed to construct the reaction boundary is one point, and the boundary slope at that point, or 2 points of the boundary. Okay, so we have, okay, no worries. So he has defined that if we will take these things as constant, then we can calculate the slope. Okay, if these things are variable, then also we can calculate at any point if this is a curved line. Okay, we have to just take the temperature and pressure difference. If the temperature pressure difference is not with us, then we can calculate from these variables. Okay, this is the slopes of metamorphic reaction. Okay, slopes of metamorphic reaction, nothing but it only describes what is the actually utility of this thing. This actually defines, like, if there is a reaction curve which is stable, which is like equilibrium, reaction curve is in equilibrium condition. So how this reaction curve moves? Okay, how this reaction curve moves, like it is a curve path or it is a straight line, that is only defined by the slopes of metamorphic reaction, and that thing is described by Clausius Clapeyron equation. dp by dt is equal to del S by del V. Okay, so this is the thing. Everyone got it, na? Okay, so next we are getting back to another law. I am telling you, this is not actually in the PPT. I will upload all the PPTs today. Before in the previous class also, the previous week also there were the PPTs were not uploaded, so I'll upload today. Another thing I am telling you that Fourier law of heat conduction. Okay, Fourier law of heat conduction. So this is a very simple law. You have already read about the what this thing hydrology. What is the law in that hydrology? That water transforms. What was that? Yes, definitely Darcy law. It is similar to Darcy law. Okay, it is similar to Darcy law. Very similar to Darcy law. Like you know, in Darcy law, Q is equal to minus K A del H by L. This is the law of Darcy. Okay, like that in Fourier also given the same law, but he has added a second variable, one another variable. Just that is the thing. So Fourier tells that, like, if these are okay. Wait, I'm drawing a new diagram. If this is a conductor, okay. If this is a conductor, this is a conductor, and heat is passing from this side to this side by conduction only, by conduction. By conduction, okay, by conduction heat is transforming, heat is getting uh, conducted, okay, it is getting conducted. Now he told that the amount of heat q conducted throughout this plate, okay, throughout, consider this as a plate is directly proportional to the cross sectional area, okay, is directly proportional to the temperature gradient. Temperature gradient means this thing. With distance, how much temperature is decreasing or increasing. Okay. So the temperature gradient, that is dx dt by dx. Okay. This is x. Okay. This is x and dt. Okay. Dt is the change in temperature. X is the length. And inversely proportional to the uh, sorry, not inversely proportional, directly proportional to the time. Okay, directly proportional to the time taken to be conducted. So we have to arrange this all things. Q is equal to minus k a dt by dx into t. This is the Fourier's law of heat conduction. Okay, so why minus? Because temperature is always transformed from higher temperature to lower temperature. Okay, higher to lower, always it is conducted from higher lower temperature to lower temperature. This is second law of thermodynamics. Na? Second law of thermodynamics, never heat can be transformed from a lower temperature to higher temperature. It is always transferred from higher temperature to lower temperature. Okay. So Q is equal to minus Ka dt by dx into T. This is the Fourier's law of heat conduction. Exactly equal like Darcy's law. Okay, exactly equals like Darcy's law. And after that, what he does, same like Darcy law, Q by A is equal to minus K dt by dx into T. Okay, Q by A is equal to minus K dt by dx into T. Then Q by A into T is equal to minus K dt by dx. Then this is heat per area in time. This is called as J. Sorry, this is called as current density or current flux. This is called as flux. Okay, flux J. Okay, this is called as flux. J is equal to minus K dt by dx. Okay, this is also the Fourier law of heat conduction. Got it? Everyone got it? It is a very simple one, like the Darcy's law. Okay. And this Q by A is called as Q, small q. This K is coefficient of heat conduction. Okay. Everyone got it, na? This is very much similar to Darcy law. Only you have add this time to this Darcy law. Okay. Only you have to add this time, because time is also there. If the plate will be so much thick, it will take much of time because conduction is going on. Okay. It will depend on the conductivity of that plate, or of that material, that how much conductivity the plate have. Okay, if the plate is a copper one, then the heat will transfer very fast. But if the plate is of a like mica or quartz, then the heat will transfer very slow, na. That is the thing. That's why temperature constant is there. Sorry, time constant is there. Okay, so these are all things. Next, chemical potential, and then phase rule and mineralogical phase rule. We'll go to that. Phase rule and these things are almost complete. What we have left in metamorphic, let me see. Your chemical potential, fugacity, activity, tracing the chemical reaction in PT space, phase rule and mineralogical phase rule, Claussius Claperyon equation, slopes of metamorphic reaction, heat flow, diffusion, and mass transfer. This thing will be told you. Heat flow you have already studied in geodynamics. Okay. Diffusion and mass transfer will be taught you in structural. Okay. Diffusion and mass transfer, and your this microstructure and texture of regional and contact mechanism, microstructure after this shear sense indicators. Okay, these all things, that things, and this diffusion mass transfer will be all in one place. Okay. Fourier's law of heat conduction, geothermal I have already told you geothermal what is geothermal. Okay, I will just upload the PPT and you will just go through. Nothing more than that is geothermal is that only. Mass and energy change in fluid rock reaction, this is the only thing remaining, and Charnockite problem. Okay, these two are only thing remaining. Okay, let me tell you mineralogical phase rule and mineralogical phase rule. So you know the phase rule, tell me the phase rule. अंकिता भूल, गलत है अंकिता, सुरभि गलत है। Okay, so the phase rule is P plus F is equal to C plus 2. This is called as Gibbs phase rule. Okay, Gibbs phase rule. This is called as Gibbs phase rule, or simply phase rule, where P is the number of phases, number of phases. Okay, F is the degree of freedom, degree of freedom. That is the number of the minimum number of intensive variables required to describe the condition of the system. Condition of the system. Okay, like degree of freedom is like, if we want to define this point, then we have to take two variables x and y. Okay, if there is a line and we want to define this point, okay, then only one variable needed, that is y coordinate. Okay, this is the degree of freedom. Okay, so degree of freedom, and c is the number of components, minimum number of components required to describe the whole system. Okay, minimum number of components required to describe the whole system, and 2 represents temperature and pressure. If any one gets constant, then it will reduce to 1. Okay, this is Gibbs phase rule. Now एक चालाक पर्सन आया, थोड़ा ज्यादा चालाक. कौन? गोल्डस्मिथ. और गोल्डस्मिथ कैसे लिखते हैं इसको, जो भी हो, गोल्डस्मिथ. ओके. So Goldsmith came and he gave a rule that is called as mineralogical phase rule. Mineralogical phase rule, or also called as Goldsmith phase rule. Goldsmith phase rule. Okay. So what he saw like in many systems, what is happening? P plus F is equal to C plus 2. Okay. Now in many systems, in metamorphic geology or metamorphic petrology, the number of components is always more than 3. Okay, always more than 3. Okay, so that's why he just smallly modified this equation. Actually, he have not modified any equation. He have just given a given a limitation to this. Phase rule is applicable only in equilibrium condition. That you always remember. Okay. Phase rule is applicable only in equilibrium condition. If there is no equilibrium, then there will be no, the phase rule will not be applicable. Okay, like equilibrium means not actually particularly equilibrium. I am telling it wrongly. Equilibrium crystallization or equilibrium melting. These things. Okay, equilibrium crystallization or equilibrium melting. This thing. If you are considering phase rule is applicable for fractional melting or fractional crystallization, this is not possible. Okay, or partial melting, this is not possible. Equilibrium melting and equilibrium crystallization should be there for application of phase rule. So now what Goldsmith did, so Goldsmith written that, where it is on, P plus F is equal to C minus P plus 2. Okay, it is not here. Wait. This thing, the phase rule can be applied as a test of equilibrium for an equilibrium mineral assembly that crystallizes over a range of both temperature and pressure. As usual, the case of metamorphic mineral assemblage, F is equal to so that C is equal to P. Like if you will put P plus F is equal to C plus 2, then F is equal to 2, and your F is equal to, if degree of freedom is equal to 2, then 2 cancel, P is equal to C. So the number of components will always be equal to number of phases if the degree of freedom is only 2. Okay, the degree of freedom is 2. Then degree of freedom is 2 where this degree of freedom represents pressure and temperature only. Okay, pressure and temperature only in metamorphic reactions. But the thing is, the only the temperature and pressure constants are not there. There are many variables. Okay, that's why he modified the phase rule, that this is not applicable as there is more than one variable of pressure and temperature. Okay, so here you see I am sharing my screen. Okay, here you can see this is the new phase rule. Okay, if f greater than 2, so f always should be greater than 2 for the multi-component systems like the composition complex systems. This is the P plus F is equal to C plus 2 is for the experimental petrology. Okay, for like they have experimented these in the lab, but in case of your natural condition, the degree of freedom is always greater than 2. There are more than 2 variables. Okay, there are more than 2 variables. Temperature and pressure is not variable. They're not the only 2 variables. Na? There are very much higher amount of, like you can say depth, you can say your fugacity. They are all variables are there. Multiple variables. Complex nature is a very complex system. If you are defining that नहीं बस टेम्परेचर प्रेशर में ही हो जाएगा तो नहीं हो सकता वो पॉसिबल। इसीलिए गोल्डस्मिथ ने क्या किया, उसको चेंज किया, बोला कि नहीं भाई एफ इज इक्वल टू ग्रेटर देन 2 तो होगा ही, तो उसको बस उसने ये कर दिया एफ इज इक्वल टू सी माइनस पी प्लस 2 ऑलवेज ग्रेटर देन 2, ग्रेटर देन इक्वल टू 2 कर दिया कि प्रेशर एंड टेम्परेचर तो होगा ही, उसके बाद भी होगा। ठीक है, एंड ऑलवेज पी इज लेस देन इक्वल टू सी। ओके, सो सी दिस वन। तो वो क्या बोला कि भाई देखो देखो नेचर में जो है सिर्फ प्रेशर एंड टेम्परेचर वेरिएबल नहीं है, डिग्री ऑफ फ्रीडम जो है इसका नहीं है और बहुत सारा का है। सो जो P प्लस एफ इज इक्वल टू सी प्लस 2 रहता है, एफ इज इक्वल टू सी माइनस पी प्लस 2 रहता है। ठीक है, तो दिस विल ऑलवेज बी ग्रेटर देन इक्वल टू 2। ओके, एंड दिस P विल ऑलवेज बी लेस देन इक्वल टू सी। मतलब जितना कंपोनेंट है उससे ज्यादा फेज नहीं हो सकता। ओके, दिस इज ऑल्सो ए शॉर्ट क्वेश्चन दैट फेज कैन बी greater than component or not. Phase cannot be greater than component. Phase is always less than or equal to component. Okay, so you should write the mineralogical phase rule. This one is the mineralogical phase rule. He have just widened the constraints. Okay, that degree of freedom will be more than 2 always in the natural complex systems, and phase will be always less than equal to c. Okay, now three cases arise. Okay, now three cases arise. What? One is P is equal to C, one is P less than C, one is P greater than C. Okay, for this thing, three things arise na. P is equal to C, P less than C, P greater than C. Okay, if there is P is equal to C, then you can say this system is in equilibrium condition. Okay, I am writing again F is equal to C minus P plus 2 greater than equal to 2 and P is always less than C. This is the mineralogical phase rule. Okay, now three conditions arise for this condition. Okay, so P is equal to C. If P is equal to C, then this thing cancels, F is equal to 2 and the reaction is in equilibrium condition. Equilibrium condition. Okay. If P less than C, okay, if P less than C, the reaction is continuing, okay, and or it may be a solid solution reaction. It may be a solid solution reaction. Okay, it may be a solid solution reaction. If P greater than C, then you have calculated wrong. Okay, this thing only written. Okay, You have calculated it wrong. Okay, these three conditions. So you can see here, I am showing you. Where this has gone. Sorry. Oh, PDF. No? Sorry. So if P is equal to C, this is accepted as the standard divariant situation in metamorphic rocks. The rock probably represent an equilibrium mineral assemblage. Okay. If P less than C, this is common with mineral system exhibiting solid solution. Okay. ये गया. If P greater than C, this is for more interesting situation and at least one of the sorry ये थोड़ा मैं गलत बोल दिया. So if P greater than C, again there are two conditions, I think. Three conditions. Okay, you did not choose the number of components correctly. Yes, three conditions. If P is greater than 3, if P is greater than C, there are three conditions. Okay. If P is greater than C, there are three conditions. One is F is less than 2. That means he is telling that this is not possible. Okay. If P is greater than C, then there must be three possibilities. Maybe F is less than 2, or maybe equilibrium is not maintained. Equilibrium is not maintained, or we have calculated wrongly. Okay, we have calculated wrongly. Same thing only. These two things I am not tell. I was like forgotten. Calculated wrongly. Okay. So this thing he is telling that this thing is not possible. P is greater than C. It will be not possible. It is not possible at all. P will always be less than equal to C. Is it either equal to C or less than C? This is the thing. Everyone got it? What is the mineralogical phase rule? Yes, Ankita.
Sir, can you repeat the last two three lines? I was unable to hear that.
Okay, so basically I am telling another time for everyone. F is equal to C minus P plus 2 is greater than equal to 2, and P is always less than equal to C. This is the mineralogical phase rule. Now three condition arises. P is equal to C. This is equilibrium condition. Okay. For this statement, there are three conditions. P is equal to C, equilibrium condition. P is less than C for solid solutions. Okay. Another condition arises, that is P is greater than C, which is not possible. Okay. So when this will be possible? There are three conditions when this will be possible. If F is less than 2, because we have defined here F should be always be greater than equal to 2. So if F is less than 2, then P can be greater than C. If equilibrium is not maintained, okay, and if we have calculated wrongly, okay, calculated wrongly. In these three cases, P will be greater than C. Otherwise, it is not possible, and this is also not possible. Okay, got it? So basically, the mineralogical phase rule is this: F is equal to P C minus P plus 2 greater than equal to 2. P is always less than equal to C. This is mineralogical phase rule or Goldsmith phase rule. P plus F is equal to C plus 2, or F is equal to C minus P plus 2 is the Gibbs phase rule. Okay. Okay, everyone got it? Okay. So